this session is to explain some unexplained features of dynamos as we observe them. I don't think in the last 10 years there has been really any significant progress on this. Let me highlight the issues. Over the last 10 years, over the last 40 years, stellar cycles have been observed on many stars. I didn't bring any picture of these cycles, but many of you have probably seen that from the body units that are papers. This project was started by Olin Wilson in '66, and so these most of these stars are measured. There's a sample of 100 stars that he selected back then in a famous paper of '67 already. And with a few years of observations, he already noticed that they show some activity. And so they have been monitored with the Mount Wilson telescope ever since, 100 stars. And in the meantime, more stars have been added to the sample. Yeah, it's being, this is completely stupid, of course, but this is being continued by other people. But as we know, there's some discontinuity. So, I mean, obviously everybody, yes, I mean, similar stars are being observed by other, but I mean, I know, for example, in the southern hemisphere, the Strassmayer is expanding this, is that right? Extending these type of observations to the southern hemisphere. But of course, in these other stars. I mean, this is, anyway, so this is something to be discussed, of course, how such a thing is possible, to discontinue something which is just so important. I mean, one has many stars which have cycle periods between 10 and 20 years, and so what point is there in actually discontinuing after 30 years if you observe a 20-year cycle period? And then say, okay, that's good enough. So I don't understand who is taking such responsibility here. But anyway, so this is a paper here which really started the theoretical understanding of all of this in '84 by Noyes, Weiss, and Born. What is plotted here is the inverse rotation period, which is the rotation frequency, and that's in logarithmic units. And then here again in logarithmic units, the inverse cycle period, which is also the cycle frequency, therefore. And you see that there are some stars which show a rising trend of the cycle frequency with increasing rotation frequency. Here is a disconnected group of 3 stars which also show that. And so this was the state in '84, and then there was a review paper by Born and Saliberliunas a year later in the annual reviews of astronomy and astrophysics. And that was then the result. So in the previous picture there was an increasing trend. And there was some theoretical understanding of why this could be. And there were, I mean, in this paper, Nigel Weiss had some ideas. This could be maybe most likely due to magnetic buoyancy as the relevant nonlinearity of the dynamo, rather than other effects, rather than outer quenching, because they would lead to a different trend. But then much of this was immediately discontinued again after this plot came out. Because while there was a clear trend in the previous picture, although it was in 2 different groups, in this case it's almost the same thing. It's the inverse rotation frequency, but here it's already normalized, made non-dimensional, with the convective turnover time. And that's typically the turnover time measured at the bottom of the convection zone from standard mixing length models. It's typically 1 scale height above the bottom of the convection zone. That's a kind of a recipe. And by the way, there is something called the empirical turnover time, and that's something that you get by minimizing the scatter in a somewhat unrelated plot. In a plot not related directly to this, but you find if you plot, would it not B minus V? Yes, I think so. B minus V, and you plot now the convective turnover time versus, sorry, not B minus V. It's of course the same number as this, so it's also a convective turnover time, and typically I would call it 2 omega tau. That's what we normally call the inverse Rossby number. And then what is plotted is simply the stellar activity. We will see actually such a plot in a moment.
It's not surprising, you know, big series of derivations.
This is Rossby.
Sorry, what are you saying?
It's not surprising because here big series of derivations and you get radish. It's not surprising. Because this turnover time is theory, it's not relations.
Okay, so what is the problem first of all? We see more scatter now.
The rotation period changes by, I don't know, factor of 3 or 4, and this turnover time is completely theoretical by all this quantum theory.
So you are saying because mixed theory with observation, yeah? I mean, we don't know, so I collect these arguments here. That's, so you're thinking it's actually bad to mix. So the empirical thing that I was about to plot here is actually a plot of the stellar activity. RHK is, first of all, the emission in an absorption line. So there is, in the calcium, by the way, if you go to the observatory, which is the 6th floor over there on the other, in the main building, there's a fairly long floor. Along the floor, if you go up there, there is a spectrum of the sun is plotted over a length of, I think, 500 meters, or something like this. And of course, that takes some time to navigate your way to the calcium H and K line. Because if you have no idea where that is, you run in the wrong direction, of course. So you need to know. And if you, of course, want to find somebody, then sometimes they say, I'm near this RHK line, for example.
It's not in the red.
It's in the blue.
It's
in the blue. I think it's 4,800.
It's in the visible
it's visible, but it's more blue than red, of course.
No, I mean, if you know where this is in length, you have to look in the visible range.
You better look in the visible, yes. Otherwise it's invisible. So RHK is, so you have an absorption line, and in this calcium absorption line there's 2 emission lines. And those emission lines are being formed in the higher atmosphere, and they are being formed by elements that have high temperatures, and that means the gas must, this hot gas must be somehow confined. And the idea is that this hot gas is being confined because it's confined within magnetic flux tubes. And so by measuring the intensity in these lines, one has an empirical proxy of the strength of magnetic flux loops above the solar atmosphere. So that's something that has been an extremely powerful tool. It can be used both as a local proxy on the surface of the sun. This has been investigated by Carl Schreiber, and we know therefore that this one is related actually to the magnetic field of the sun, to the local magnetic field pointwise, but in units of the, let me write it, in the units of the equipotential field strength. Raised to some power, which I believe is on the order, first of all, it's magnitude, and raised to some power, and either it's 0.4 or it's 1 over 0.4, I forget which the exponent was on this side or on the other side. But this is maybe you see it later on in one of the terms there. This exponent we call in our papers typically kappa. So now what is then seen here is that this curve looks like this, and this is well known. And then I was talking about minimizing the scatter by using so-called observational taus. One means actually the following. So although this tau was primarily taken from the stellar evolution models at one scale height above the bottom of the convection zone, you find a certain scatter, but then you can actually plot another curve. Oh, I guess I know what it was. So now it's B minus V. And you plot then.
This is B
minus blue minus V is blue minus visible. It's a color. So it's basically the same as a measure of the stellar mass, because we're talking about main sequence stars here all the time. And then it is essentially this tau correlation, or convective, or conv, that's what it's called. And that shows, so as you go smaller towards smaller mass, the times become longer. So I think this curve must look like this. So you can come up with an empirical curve by minimizing the scatter. This I've done myself. And so this improves somehow slightly such a thing. That's what I wanted to mention in parentheses.
Because it's not a theory, not observation, it's just prejudice.
Sasha, could you speak loud?
So I'm saying, so I mean,
observational.
So you so you minimize the scatter, and so in that sense, he is saying this is actually worse. But the question is worse in what sense? I mean, what is our goal here? What?
It's a prejudice.
Yes. I mean, so therefore, actually, I think Baliunas and Vaughan, they were saying from observational point of view, this is sort of much better because there's no prejudice in it. But you say there's already too much because there's already this knowing. So
no reason for doing this. Except again.
Yes, I mean, but first of all, there was a conflict from the previous plot to the current plot, in that we had increased the amount of scatter. So the first step, when I entered this game in '98, was to do the following, and let me go to the following page instead. So we took, with a student at the time, these data. Here's, by the way, this B minus B. These are the stars from the paper by Baliunas and a number of co-authors, all published in '95. This was a long paper. Now this had, as I said, 100 stars on it, but all these stars, they actually had a quality parameter. There's this parameter which is called FAP. FAP, and it means false alarm probability. And I believe this language is being actually used in other observational fields. So it's something which the observers take quite seriously. And so...
What does it mean?
You mean that your detection is perhaps not reliable?
So, and then there was an additional parameter which was a quality parameter. So what we did, first of all, we threw out everything which was not excellent, and in the second level, still good, or very good. So we only took those stars for which we actually know with certainty the cycle frequency and the cycle period. Because if you have a sequence, for example, which looks like this.
I mean, have you looked at the actual data? Because they never release the data, you know, that's one of the problems.
Yeah, but they do give...
Because data are not released.
No, in the Baliunas paper, I think there is some...
No, that's observation data.
I mean, what Sasha is saying, that there's much more behind it, of course, because...
The raw data?
In order to come up with a false alarm probability, I mean, those things I have not checked myself. But I thought it's a good idea. So first of all, the periods are being measured using some period analysis program. And of course, if you measure the period of such a signal here, where there's first of all a trend and the amplitude is changing, you can force your program to release a period, maybe between here and here. But then it will give us that the quality of this is not very good. So this will come out of this program.
Look,
and I think this makes a lot of sense.
That data or not? That's the Baliunas 95 paper. Can we call that data?
Well, we need to like jobs, you know.
Yeah, but there's more more to that, of course. We should have maybe really. So one of the things that she's showing here is the S parameter, which is actually emissivity, which is not this one. And from this one and the same signal, namely this signal or the original S parameter, you get two things out of it. You get, first of all, the long-term oscillation, which is over a period of 30 years, up to 30 years. In addition, you get the rotational period out of this from the same data. From the same data, you get the rotation period. And most of the times, the rotational period is much less well determined than anything else, than this one, for example. So there could be easily, you could have a star at your hands which, where you get the rotational frequency wrong by a factor of 5 simply, because you just overlook things. I mean, the way that you do this is by taking basically the sun and saying, okay, here is a certain frequency which I interpret as being due to a sunspot. And then I get my rotation period out of that. That's the only way that you get rotation periods out of this, simply by measuring high frequency oscillations, which are sufficiently regular. And out of this you get the rotation frequency. So it can easily be wrong by just misreading the data. And so only if those data are very certain, I was taking those into account. Right. I mean, the observers tell me that they are certain. Right, because that's in their paper.
Yes, we give you all bars. It's a very serious paper, the Ballunas paper. We did a very good job.
So we take these error bars, and then the error bars are sufficiently small in respect of quality and false alarm probability. We take those data into account. Here we have all the stars. Here we have all the B minus Bs. 0.567 is a very blue star. And these become reddish. And so the latest is this one here has the color of 1.37, which is very red, and it's an M star. And if you're watching these M stars, you may wonder why don't you have more? It's quite sparsely populated. These are, by the way, ordered in B minus B. The reason is, does anybody know why you have so few stars over here?
Because they are dimmer.
They're dimmer, yes, exactly. So therefore, it takes actually 1 hour, exposure time. It takes 1 hour exposure time to measure such a thing. And so in order not to spend the entire night on those few things, you take few of those and then do the rest. So here is then the rotational period. It varies between, in the shortest case here, between 10 days and all the way to 40 days. The cycle period in years is typically between 7 years all the way to 21 years. Here then the correlation times or convective turnover times, and here is the logarithm of RHK.
The correlation time comes from model.
Yes, yes.
Less than
It comes from the model. And it can be improved. This quantity can be improved, as I explained before, by using instead what I call an observational quantity, namely one which minimizes the scatter. So it's basically giving you a means of saying that if a star rotates fast or slow, it matters whether the star is at the same time a big one, a high massive one, or a low massive one. So if you take a rotational period of 10 days, Sasha would be saying it doesn't matter. I mean, if it's 10 days, then this is observational. I will take that regardless of whether it's an M star or an F star. Whereas I would be saying I mix this with models, and I would say instead of taking this 10 days as my basic quantity, I'm taking a non-dimensional quantity, which is inverse Rossby number, which is calculated in the best possible ways as we can think of. Yeah, but it's basically
around, you know, that is, so that's
it's basically a monotonous scaling function. It's a monotonous scaling function.
no. What I noticed when I showed this plot, it changed by orders of magnitude, like 5 orders of magnitude, when you show this Rossby number. But you know, rotational period changes by factor 3 or 4. Here. You see, you have what?
But it's not.
No,
it's a one order of magnitude.
Yeah, this is less than order of magnitude here.
Yeah, I didn't see points. Yeah.
Here is an hour data.
Yeah, but still, it's
It's certainly much less than an order of magnitude. I think it's good to plot things logarithmically, because that way you can get slopes out of this.
But usually observers, they don't mix the series, but
Exactly. Yes.
But the argument behind that is that it's more important for dynamo to have a relation between convection and rotation than just taking rotation, because we know that dynamo is not just based on pure rotation rate, but there is an underlying process that involves convection to generate the field. That's the reason why you are trying to normalize that by the time scale of overturning time of the convection of the stars you are considering. So there is some physical argument behind that. It's not just silly things, you know.
Se meni ihan väärin. Mitä katsoa, mihin se menee? Onko se oikein nyt?
But usually they are using the 1D model. They were using a 1D model that was for the sun calibrated as best as our knowledge, and then they were extending using the same mixing length parameter. They were computing other type of stellar model for different spectral type, and we are using the overturning time of convection we were getting for this model to scale. So there were some, okay, of course, procedure, but done in a systematic way. And you can object that, but it was not.
I mean, you could do the same thing with. You can do the same thing with theoretical models. You can take theoretical models and compare a large. I mean, you know that things depend on Reynolds number, right? But Reynolds number is what really the thing depends on. You can then take big ships and small ships, which have the same Reynolds number, completely different. And of course, the same shows the same physics. And now you can afterwards mess everything up completely, and simply say this is just the observations. And then of course you have a box with points everywhere. And then you can say, this is what we learned from observations. We know that everything is possible. That was the conclusion back then. So the conclusion was that there's no systematics in that. The question is that a fair conclusion or not? And so here you see the results. So now we are back. We have two clean branches.
Yeah, but you have without these branches and all that here, just to plot
They don't.
cycle period as a function of rotational period. This is a paper by Von Wittgenstein a couple of years ago.
Yeah, but that's because they were referring to us.
These two populations.
Sasha, but what is your alternative?
Oh, you just don't scale this, convective overturn time, just plot as a function of rotational period, and to get same dependencies. This was paper by Von Wittgenstein a couple of years ago. She found these two populations, and the sun was between these. That was puzzling. Huh? Yeah,
So I'm wanting to find the paper where this was not done, and then you can see what else you can get. I think it was
I can show this.
probably even here. You want this? You want this in the meantime?
Yeah,
But this is not long enough.
maybe I don't understand correctly.
The cable is not well located.
I can see this cycle and period of rotation, the populations.
So what
Exactly.
is
Exactly.
the Von Wittgenstein one? It's here, the Von Wittgenstein, okay.
2007.
Okay, I'm getting now.
Yeah, but have a look again. What is the slope? I mean, remember I was talking about something was increasing, right? Can you tell me whether it increases or disagrees?
No, you can see the populations and some between these. So that's interesting.
Yeah, but do you know whether it agrees or disagrees? That's my question.
What do you mean degrees of difference? I don't know what the observational facts are. Here's the observations, you can see clear trends without scaling the theory.
Yeah. But you know, Sasha,
No, but show again. Huh?
if you
Show again. Did you actually look at the plot carefully?
you don't know if you plot in this way, is it fast rotation or slow rotation?
What do you mean fast slow rotation?
In comparison, for example, if you plot Coriolis parameter or Gauss-Rossby number, you know it's fast or not slow rotation.
Okay, so here you see period. Yes.
The conclusion because it was logarithmic for some reason, but without logarithm it's kind of
sun is here. Isn't that weird? Anyway, but anyway, I think the slope is increasing, which is probably okay, and you do see the gap, yes. That's correct. Now I'll show you something else.
No, this is consistent with the results.
It's consistent, but here's something else, which, because I didn't, but this was the paper by Böhm-Vitente, yeah? Is that right?
What is?
That was the Böhm-Vitente paper, yes, and of course they were, so here's another plot. So here's one of our rotation period, and cycle period upstairs. And again you see a positive correlation. Did you know that? Do you see that there's sort of contradiction now? So one of our rotation means frequency. Again, it's logarithmic. But in units of, I mean, how can you ever make a logarithm of something which has a unit? What is the logarithm of a meter?
I don't know.
You don't know that? No. And so here what they have, here's non-dimensional, and here's the ratio. So this is the cycle frequency upstairs now. So what you now see is that the cycle period, that the cycle period increases with higher rotation frequency. So that means that the rotational frequency, the cycle frequency, which is inverse of this, decreases. It decreases if you plot this the other way around. They have really mixed things here. So now let me compare with our paper. And so this is what it is. So you can of course mix, such a have a look. You can of course mix these two branches together, and then you find a line which goes like this, because it's essentially a slope down here. That's what this other plot was. It had a negative slope in this plot actually. That's what it is. So I think that's important to realize. By mixing everything together, you can completely alter the conclusion. And now the question is, which of the two makes more sense? To mix big and small and just to say rotation is all that matters for the dynamo, or is it somehow the non-dimensional thing that matters? I mean, in that case, you could say millisecond pulsar, which a neutron star, which produces convection and produces magnetic field on the time scale of a millisecond, is something completely different because it's millisecond as opposed to days for the sun. And of course, from a theoretical point of view, the opposite is normally what people say. What matters is the non-dimensional quantities, the relative ratio of rotation to convective turnover time. Okay, so here we have now, again, these two different branches. And in the previous plot, they were mixed. And so in this previous plot, there was no one-Preston gap. So when Sasha says it's well known, indeed it's well known, this gap has a name. It goes back to one and Preston. And then there was a time in the 90s when it was argued the one-Preston gap has disappeared. And that was this other plot, which was then repeated by many other people. Here's this. Do you see a gap here? You must somehow see a gap between here and here. And that's called the one-Preston gap. And then there was people who said, there's no gap, and so they said this famous one-Preston gap has disappeared. And that's simply by mixing up big and small stars in an arbitrary fashion. Okay. Okay, so this was the conclusion here. By the way, you see another thing. If you now plot the plot that I was sketching up here, RHK versus the rotation frequency, that's the same thing here. It's inverse Rossby number versus RHK. Again, you don't see a gap anymore. All these stars are on the same line. So these different stars, which have which are on two different branches in such a plot, they happen to be in the same line, and this has a slope of 1. So this is the activity versus inverse Rossby number. It's the same plot as this. The difference is, we know if we go to more active stars, this line actually saturates. And that's not visible for these stars in this plot yet.
Rosby number doesn't play any role.
I showed you this picture. That was not the same. Was it the
After
same?
after defeating, convective turnover time.
We have the same thing in our paper with SAR. It's not the same. It's the opposite conclusion.
So what's your turnover time and the function of rotational period? Do you have this plot?
The term in terms of convection.
But they are not related to each other, of course. This would be also plot like this. You can have stars which are rotating fast and slow, and the mass is not related to how fast they are. Therefore, this is such a plot.
But after this, you did some fitting.
Yes, exactly.
And then write the scatter.
Absolutely.
When
Of
you
course,
do
and then you can do a
already
fit.
know the function of mass.
You can do a fit like this. You can also do a fit like this. Or you agree
But
with
you
that?
fit to minimize cut on this plot, right?
Sasha,
The scalar, we calculated the scalar. We have done the comparison between dimensional and non-dimensional ones. The scalar in these plots is less.
Sasha, could
But the conclusion is completely
Could
different.
you explain why it doesn't have any relations? I mean, the Krivulus number or Rosby number.
Oh, because it's not, because first this turnover time is a Mitchell theory, right?
And so what?
Why Mitchell theory is related to dynamo?
Just wrong. This is
No relation there.
roughly.
Now you are
this model
extreme.
works very good.
So tell me one thing which is not correct in mixing link theory. There's probably, but name me some of them.
Mitchell theory.
Yeah, what is not correct in mixing link theory?
Everything's incorrect.
Everything is incorrect.
So velocity is incorrect, velocity is incorrect.
Convective velocity is
Structure
incorrect.
convection is incorrect.
What do you mean by convection as opposed to convective velocity? What do you mean
In
by
the sense, of course, mixing
Oh,
lens
convection
theory
is-
doesn't take into account rotation, but nevertheless, this theory works.
yeah, but
Look at, say on the sun, we can see convection on the, we see granulation, right? We can see supergranulation. What can lens theory tells us about this? If you look at the just velocity, just measure Doppler shift, right? You can see the down drafts, down drafts.
Well, there is a
You see
there is a
down,
difference between.
downward
No,
velocity.
no,
vector theory,
Sasha, you have to be, of course, you have to be fair with the mixing length theory model. The mixing length theory model is telling that you have one scale, and that scale is proportional to alpha, the mixing length parameter, times the local pressure sky height.
That's the
Alpha,
first
there is
thing.
alpha. So of course, as you get closer and your HP gets smaller, you get smaller scale, but you will not get multi-scale. By definition of the mixing length theory, there is only one scale. That doesn't mean that because you're only considering one scale and not a spectrum of scale, that the actual amplitude of the velocity is wrong. And when you compare 3D models to mixing length model, you do find that there is a difference between the mixing length value and the computed value, but there is one constraint, one big constraint, is that luminosity of the star, if it's carried by convective luminosity, you can write your convective flux, and your convective flux, is proportional to rho v cube. So, since you have a star of a given luminosity, and this flux is proportional to rho v cube, no, that gives you a value of v cube. And that gives you a value of v cube, and v cube is v cube. I mean, you cannot play with that since you have a constraint with the luminosity.
There's no relation to dynamo. Excuse me.
No, there is very strong
is
relation,
that-
Sasha.
So the relation is that convective velocity is the flow that will get into the EMF, okay, which is v cross b, okay?
I mean, we all agree with you. But Sasha needs to explain why you are making such a fuss. Can you explain that?
I will say, just supporting this idea, because we know that,
Yeah, but we know this all.
just move. We know that main contribution from turbulence to the dynamo coefficients comes from the maximum scale of turbulent motions. And spectrum of turbulence is not so important. In that sense, mixing length theory works very roughly, and
Well, we know
yeah,
dynamo.
just more. But why it's important to compare with rotation rate with correlation time. Only this parameter can say us if there is fast rotating or slow rotating convection turbulence. And it's very important. If it's fast rotating, so it's nearly two-dimensional, or looks like. If it is not, it's slow rotation, it's 3D turbulence. And in that sense, it's very important to compare with this time.
But let me explain you what when people look at the sun,
Can you come to the
the best. No, I don't need to show. So when people look at the sun, we know that the dynamo is, it's kind of, that magnetic field evolution is controlled by supergranulation. At different regions, some spots that appear magnetic flux emerges with boundaries of supergranules, and the diffusion of magnetic flux will determine the length of solar cycle. It's in Layton's papers in the 60s it was found. It is controlled by supergranulation. Nothing in the mixing length theory tells us about supergranulation. So if you want to make it, should compare with, say, supergranulation time, that would give a parameter.
Doesn't imply
But
your
it's still,
statement that
that's a
I think that's a
doesn't imply the statement
misunderstanding.
that turbulence doesn't play any role.
I didn't say the turbulent, but I say mixing length theory, had no relation to dynamo. That was my statement.
No, the turbulent diffusivity, DT, has to do with RMS velocity and the length scale, right? The length scale decreases as you go downwards, this is now radius in stellar units.
Mixing length theory, there's no scale, at all, that's just a pressure scale height, changes with depth.
There's no scale, you say?
Mixing length theory, yeah. It's all density scale height, or pressure scale
Yes,
height.
yes.
It changes with
Yeah,
depth.
but what do you have to
depth you choose.
you explain again? What do you complain about this one? This one suggests that the size of the conductive cells scales with HP.
So what is HP here?
Pressure scale.
It's just
Where?
At
Okay.
Where?
At
Where?
some R.
Functional form.
It's at R.
Okay, for which R?
Now, any of the R's you choose.
Well, I change it by, three orders of magnitude
Yes.
in this range. So which I choose? Then what when I do this, when I make this plots in this here.
I choose this one, I choose this one, I choose this one, I choose this one. If you want me to choose this one, I choose this one. I choose all of them. It's a function. And now the prediction from mixing mix theory is that the scale of the convective eddies has scales with this quantity.
Okay, so when I make this plot, what is the convective forward turnover time at which depth?
Why do you ask this?
What?
Why do you ask this? My question was
Because
whether it's borne out by
uncertain.
simulations
It's
or not.
uncertain. There is no such value, that's in this one theory. It all depends on depth, and it depends on how you choose this. You make a plot.
That's what I'm saying. It depends on depths. And so at different depths you have different HPs, and at different HPs you have different correlation lengths of the motions. And you ask me now whether
I'm
it's
asking
borne
you
out
your
by
plots,
simulation or not.
how you choose depth in your plots.
I mean, it's a function. If you want to plot y versus x, right? If you have y is equal to x squared, how do you choose x? X can be small and can be big. So that doesn't make any sense, or what are you telling me here?
No, I'm just wondering how we choose.
I mean, we have a dialogue here all the time between you and me.
Your models.
You are asking me, I really want to know why are you complaining about this, or why are you complaining about this here?
Because it depends on radius, and I want to know which radius you choose when you make these plots. That's all.
You choose the radius of the stuff?
Does anybody
It's
understand?
changed, from let's say 100 megameters to 100 kilometers on the sun, right? So which?
Of course, in some science, there is a big point here. Of course, because HP is a large-scale quantity. L is a turbulence quantity. And of course, here there is some small parameter. If we would like to have a separation of scales. There is a weak point here, but nevertheless, this is what we have. If you can suggest much better, it will be excellent, but for estimates, this is what we have now.
Yeah, but we have already comparison with three-dimensional models.
Yeah.
And we need to know, does it
because
disagree
I
or
want
does
to
it
ask
not
question
disagree?
of this, at which R you choose this, in this plots. That's
But
all.
if we have a distribution of density, of course we can calculate its
You're not asking my
exponential
question,
behavior
Robert.
like z divided by h p. So, and this is a function of z. We have from the model distribution of density, So we can estimate HP
this
as a function of R.
Okay, this is H. I thought HP here, right? HP is this function, okay? Here it's 10 to the 10 centimeters. Here it's 10 to the 7 centimeters.
Yes.
So which are we choosing in this plot? Just answer, you know, where?
The ones that reduce
that
scatter.
changes.
Yeah,
The ones that reduce scatter.
But then you have complete freedom.
That's
meaningless.
Choose just.
No, it's not freedom because, of course, I understand that we speak about global parameters here, and these are some local parameters that strongly depends on the height. But maybe it depends on the we choose depths in the convective zone, which is relevant to this phenomenon.
Because they turn over time, you know, example, you know, say rotation a month, you know, the basic convection zone, and a few minutes at the top of the convection zone, right?
Yeah,
So which turn over time you choose?
Couldn't
No,
we
no,
just
that's the
stop
question,
the
right?
discussion that Axel
Yeah.
continued
Yeah.
to say?
So we have come here across two possible conflicts. Let me
That means that
highlight
because I
the
don't know
first
which
one.
value, you know, you can,
Yes.
when I can start
It
it, you
depends.
anything like.
So we are here at a certain depth which is close to the surface. We have a small HP and we expect small scales. So you are saying you can actually expect anything you like, but I would say we say a certain scale here.
So choosing the surface, you know, that's all I want to ask, you know. If you
Yeah.
choose
So now we
time at the surface, which is now 8 minutes.
yes,
That's
exactly.
fine,
So,
yeah,
so I've chosen now this value here. Next I choose this value. Is it true that we can get everything we like? What will be the scale, the typical scale? Will it be smaller than this, or will it be larger than this? Or will it be the same?
In Michelin series, it's larger.
With what?
It's larger,
Why?
different.
Why?
You know this from simulations.
Yes, of course. And the
Stein-
people were very...
normal, Stein normal.
Exactly, exactly. Were they surprised about this? Was this a new thing? So now they could say, oh, we made a new discovery, something which people did not expect. We find larger scales at greater depths.
This was known for many years.
It was known for many years. Since when?
Our first simulation Stein normal.
Yeah, and before that, it was not known?
No.
It was not known, yeah?
Yes, we've seen.
It was only known that you expected this.
Yeah, but no, it was not known.
Yeah, but
This
mixing ring theory happens to be completely coincident with the numerical evidence. That was the first piece. I mean, it's possible that, as Sasha is saying, that the fact that there's a relation between the two has nothing to do with the fact that the pressure scalar changes. It's just a coincidence. That's a possibility. There's a second point now. Let me find this plot here. Here. And that's again as a function of height. What is the RMS velocity? What is the RMS velocity at any depth? Do you know this? You can, of course, look at simulations and then you can get me a table. Is there no theory for this? Such I already explained. F convective should scale.
Yeah, but there's no relation to dynamo, you know, that's what I'm saying.
Let me come to
EMF is proportional to the
Actually, all I ask, you know, excuse me, all I ask, you know, what how you choose tau c in these plots, you know, that's all I ask. Because it changes by orders of magnitude in the convection zone. If
Yes.
you choose, you know, put your dynamo in Tefek line, that's fine. Tell me that you choose a Tefek line. If you put it on the surface, you choose on the surface, you know, that's all.
These are all functions of depth.
Yeah.
Now, again, this was a plot from that I showed from. I've looked at these two depths.
What the depth here?
Okay.
You have 20 megameters depth and
Okay.
1 megameter depth.
Okay, now it's
Okay, Sasha.
And of course, it's a function. It's like y is x squared.
no, if you say 20 megameters depth, you know, it's fine.
How it's dependent with the dynamo. For example, alpha can be estimated as omega, rotational frequency, L squared, this is correlation length, divided by with density stratification. This is estimation for alpha, which works very good practically in a main part of convective zone, because if we calculate here Coriolis parameter, here, okay, it's 10 to the minus 4. Okay, and only near the bottom of the convective zone, so it's implied that this is slow rotation. And this estimate is very good. Okay, here, only here, we have fast rotation. Here parameter omega tau c in the sun about 10. So this is fast rotation. Okay, fine. For this, we have another estimate, like turbulent velocity at that scale, which also can be taken from the model. So in spite of rotation, since rotation is slow in the sun, mixing length theory yields enough good, okay, it's roughly speaking yields correct results. Only here we have to.
So your dynamo works at the surface, right?
No, I haven't said about this. Said dynamo works at the surface. No. I only would like to say that in the main part of convective zone, if we use Bixen length theory for estimation of parameters, turbulence parameters, it works less or more good. That's it. Okay, where there is dynamo here or here, it's another question. But we speak about the Bixen length theory.
I started off I wanted to explain a puzzle, which is not explained by theory. So nobody was ever suggesting that we do have a conclusion about how the dynamo works. But you had a conclusion here, or not? Did you
No, I don't have a conclusion.
That's fine.
I'm just wondering
Because I
what
also think that there
the
is no
same star
conclusion
changed
as
by,
far as that's concerned.
5 order of magnitude for the same star, and you just plotted for different stars, so I was just puzzled, how I do this. That's all.
So mixing length theory makes 4 different predictions. 3 we have here, and the 4th one was erased, which was the temperature correlation. It makes predictions about how the RMS velocity is scaled as a function of depth, namely it's proportional to the convective velocity in some units, rho sound speed cubed to the 1/3 power. This is non-dimensional. Do you know what the factor is in front of this? It's on the order of 10 to the minus. Maybe I'm not right here with this. I think that's right. I think the RMS velocity scales. It scales with the convective flux to the 1/3 power, but the coefficient is very small in front of this, and that's why it is impossible at the moment with any simulation. I would state this at least to really reproduce the sun because of this very small coefficient here, 10 to the minus 11. I have that actually in this paper here to show you.
I don't know how I get this.
I'll get this. Just take the numbers.
In your plot, just before you changed it, it was
I
saying
know that
to the 2/3 power you were writing.
The flux of the sun in units of rho and sound speed to the cubed is 10 to the minus 11. It's a very small number. This has to do with the fact that the convective motions are very, very slow compared to acoustic timescales.
Subsonic.
0.2 is the density at the bottom of the convection zone. Sound speed is 200 kilometers per second. The flux is...
Oh, yeah, the bottom, yeah, the velocity factor, 0, yeah.
So this number is very small.
Yeah, 0, yeah.
0?
No, the bottom convection zone.
I mean, if this number is 0, then this means the RMS velocity is also 0.
Yeah, because the
It's
flux
not
is
0.
transported by radiation then.
So the RMS velocity is
just a wrong pronunciation,
throughout the entire convection zone obeys such a scaling law. It's not 0, it obeys the scaling law. If you disagree with this, please show me a data point.
It's, you can scale with Michelin theory, and it's more complicated than this.
So mixing length theory predicts.
Essentially, the scaling, the mixing length theory is a scaling theory.
Of course. The
Exactly
question
for
is
this- exactly for this purpose.
Yeah, but you were starting by saying it's all wrong. It's all wrong,
No, no, no.
including convective velocities, including length scales. So there are 4 predictions. If there could be a 5th prediction, I was asking you what is wrong.
I never said it for
So there could be something. Let me know
couldn't
it.
you
That is
continue
wrong.
this in private? I feel abused here. I must say I don't like this kind of procedures. Let
So then- so-
Axel go on with his
I will
presentation and keep quiet about other things.
So the plot of the
Well,
convective flux.
Axel, listen to what Fritz says, so let's move on
Yes.
to your presentation on the next slide, please. And you will end up...
Okay.
sorry.
Yes, that's fine. So here we have. So we have these stars, we have the scaling. The question is how to interpret this. One interpretation was suggested by us, and let me come to the yes. So this is essentially the same plot as before. But what we have argued here is that RHK is at the same time also an indicator for the age of the star, which is conventionally used. And so we should expect, therefore, that young stars would be lying over here, and older stars should be lying over here. Suggesting, therefore, a possible evolutionary track on an activity line, where the cycle frequency decreases as the star becomes older. Then there's a discontinuous jump by almost an order of magnitude, factor of 5 or something, towards higher frequencies, shorter times, and then going like this. To give you numbers, first of all, the Sun is one of these stars, which I now forget which one. It's one of these here. And even the Sun is, of course, so this period here, for the Sun, this corresponds to 11 years. This then here corresponds to something like 88 years, or 80 years. And that is often referred to as a Gleisberg period. So it's possible, therefore, that these higher long frequency modulations is something which actually has a direct correspondence to the lower branch here. And multiple frequencies are routinely reported in the paper by Baljunas et al. So they have the correspondence between these 2 different branches. So that's not even they're not even a completely disconnect, but they may be operating at the same time, according to that interpretation. If you think the Gleisberg cycle is something that is indeed operating at the moment, then this would correspond to some kind of physics that you don't understand, which is operating on this lower branch. Now, after that, okay, so to put a little bit more meat into this interpretation, let me put this back into dynamo in the context of dynamo theory. We make a very simple theory without any dependence on we just assume a uniform scale, a uniform wave number of the dynamo mode. And we furthermore assume that the model is nonlinear in the following sense, that alpha scales with the magnetic field strength to some unknown power n, and it's scaled at the diffusivity, the inverse correlation time we take as a diffusivity, scales with the magnetic field strength also to some other power m, which you don't know. And then we put this into a zero-dimensional dynamo model, of which the equations are written down here. Some of you may recognize this immediately because this is essentially the linear dispersion relation. So this is the real part, and this imaginary part of the dispersion relation. Imaginary part tells you the rotational frequency, and this one is essentially the diffusion term from up here, and is balanced against the generating term, having to do with the alpha effect and the differential rotation, all in one parameter collapsed, and is under the square root.
What is the M?
Scaling.
What is the M?
These are very unknown terms.
What is the value of M?
We come to that.
Okay.
That is one of the outcomes of the theory now. I mean, of this interpretation. So what then? So this, of course, then can be related to the observations. The observations tell us something about the dependence of the inverse Rossby number or the Rossby number as a function of RHK prime. Again, these exponents kappa enter. Kappa, I said already, is 0.4, and the cycle period can be related to this. So those are the relations that you can directly derive from this. And this table shows us these results here. So the answer to your question is given here. M has different values, and it depends on which of the branches you are. So I mentioned already, I didn't explain this actually, I think, that there is these two branches we have given name to this. We have called this branch, in agreement with previous usage of this name, the active branch, and this we call the inactive branch. And then in addition, we mention in this table new data. Let me show those here. So here are again these two old branches. One is the inactive branch, on which the sun lies. Here's the active branch. Here are somewhat more stars taken into account. This is in a subsequent paper by Steve Saar and myself. And he has taken into account a number of other stars, which include close binaries and even contact binaries. And those stars also fall on one of these lines. Again, the Gleisberg cycle, this I think is here the sun, and this is the Gleisberg cycle period here. And many of the other stars also show multiple frequencies.
So you say that the super branch is mostly due to binary system?
It's many of them are binaries. Some of them are single stars. There does not seem to be any dependence on whether the star is binary or not, which is very surprising. Obviously, if you are in a binary star, the star has a much larger rotational frequencies, typically of 2 days or something, and it's but other stars also have, single stars can also have 2 or 3 days, and they typically fall on the same scaling of the cycle frequency relative to the rotation frequency. So as far as we can say, based on the fact that even stars which you think should not physically be put onto such a thing, by the way, even if you put the Earth onto this, if you were to put the Earth with some typical reversal time, it would lie down somewhere here. It does scale with this. And the one thing I wanted to put on here is a result that goes back to Bérangère Dubreuil, and she has been with collaborators arguing that the Cadarache experiment shows reversal times, and that these reversal times scale with the difference of the frequencies between the two propellers. That you can interpret, that frequency difference you can interpret as a measure of the Courier's frequency. And if you do that, again, the reversal times of the Cadarache experiments, so she is telling me, lie also on this branch. So there could be evidence that we have no clue whatsoever at this point, suggesting some universal scaling of various completely amazing dynamos, which go all the way to the Cadarache experiment, to astrophysical dynamos, some of them could be even planetary, but other solar and
let's go back to this S branch. You mean that the S branch, if I look at the top line, we seem to be plotting ages. So we populated this only by age. These are very young systems.
Yeah, but the age is normally only inferred from other measures like RH. Okay, in some cases, but not in all, because not in all stars you can actually measure the calcium lines. They are not the same always. So you have to use various proxies.
Maxim, could you please show previous slide with the page?
Yes, sure. So in this table we have also the superactive one.
So you determined M and N from what? You determined from simulations?
From of course, from the observations.
From the observation.
Using this very simple interpretation. I should point out that Steve Tobias has been challenging this interpretation on the grounds that that if you take a one-dimensional model, it disagrees with the zero-dimensional model significantly. However, if the alpha effect and the eta effects are functions that are strongly weighted towards contributions from low wave numbers, this interpretation remains still correct. And this means essentially that if you argue that alpha and eta are not multiple factors, but they are integral kernels, which are strongly weighted towards the lowest values of wave number, then our interpretation is correct. And so subsequent papers, first with Dimitri and then with Karl-Heinz, have confirmed that, at least qualitatively.
And where is here sun?
The sun. The sun is on the inactive branch.
Inactive, so 4.75.
Yeah. So note in particular that n is positive for the inactive and active branches. That means the alpha effect is actually increasing with field strengths. Alpha effect is increasing with field strength. It's anti-quenched. And the interpretation back then was to say that this could happen if the dynamo, if the turbulence in the dynamo is driven by the magnetic field primarily. And such situations, of course, we were quite familiar with at the time. Those were the cases of MRI-driven dynamos, where the turbulence that leads to the dynamo comes from the magnetic field itself through magnetic rotation instability. So we called those magnetically driven alpha effects. MRI is one example, magnetic buoyancy is another example, where there's a paper with Schmidt, what's his name? Peter Schmidt, and myself. Once you come to the superactive branch, you have positive quenching, negative fixed point. However, the diffusivity is in all cases has positive scaling.
In principle, this is debates in agreement with our estimates which we made with Michael in 1995.
Yeah, okay. So that was all right.
From theoretical model which takes into account evolution of magnetic helicity.
Yes, so you also have anti-quenching.
No, I just want to say that M is of the order of this.
Positive.
Yeah, positive, yeah. It's a positive, yeah.
So it's increasing with field strength.
Yes.
Yes.
Yes, exactly.
Yeah.
I can show you.
M, yeah. And that's M was the diffusivity. And N is not explained, I think.
Okay, N, I will suggest.
And I mean, in hindsight, this interpretation about magnetically driven alphas, I don't think we have really found any evidence where that is actually confirmed. So even though you have an MRI-driven dynamo, in those cases too, I actually think that the alpha effect decreases with increasing field strength.
What is the definition?
It remains a puzzle.
N is the exponent in what law? N.
N is in the quenching of alpha.
Ah, this. Okay.
So first line on the left.
But how do you saturate then the dynamos in those cases?
Oh, it's being saturated by the diffusivity because the diffusivity also increases and it increases faster. So that comes from the fact simply that these numbers are always bigger than those. So the diffusion always increases more quickly than the alpha effect increases. That's how the dynamo saturates. The dynamo is a nonlinear one. It is saturated. So the fact that it does saturate is built into the model. The model is primitive, but it does saturate.
Is there any simulations which
No.
bears out these facts?
No. Nothing whatsoever. I mean, there's no simulation which either it suggests that the branches should be increasing. It only comes from these simple models. And there's also no idea, even, why there should be different branches. I mean, naively, you could expect there could be dynamos which could operate in different layers or something like this. But this is a stranger interpretation because whenever you have multiple layered dynamos, they really constitute one and the same system. And so there's no real good interpretation for, it doesn't make sense to consider such a multi-layered system as separate dynamos.
In the sample, you don't have any star that would show variation of P, difference rotation.
Differential rotation.
Yeah. I mean, the
That is
rotational period is fixed. There is no variation in the photometrical, I mean, the BV or something. I mean, that's how the people used to derive the amount of absolute difference rotation from photometry as well.
yeah, of course.
Yes,
But
in this sample there is no variation of P.
but it is being built into the theory.
Okay.
So we have an assumption that the differential rotation scales, that's exponent Q here. So Q is an exponent that we take from observations. However, the observations suggest that Q varies. In this table is probably a certain value for Q assumed. But Q of course enters. And
Yes, but I didn't see any estimate of the observable Q. Is there any observation of the Q? I mean, differential rotation, I mean.
I think we used, I must have checked what we used in this table. But I think the most plausible statement to date is still to say that Q is -1, I believe it would then correspond to. In other words, alpha prime scales with omega to the -1 power. Yes. So that means, is that right? What I really mean, let me see.
Yeah, that's
no, sorry.
Yes.
What I meant is that this is independent. 0, omega to the 0th power. So in other words, the absolute differential rotation is essentially constant. And that is a statement which is borne out by 4 stars for which it's very well known. These are stars which include the Sun. It includes AB Dorados, and it includes
there is a
two stars
larger
by
sample than
Barnes.
4. I mean, there is
What?
80 stars. I mean, there is a larger sample than 4, and they also all indicate a more shallow.
There's a huge number of other stars.
So it indicates that,
0.3.
something. I mean, slightly increasing trend as function of rotation rate. So other way around.
Plus, you mean?
Yeah.
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 That could be. Yes, I think it's plus. Yes. Yes. So we assume, and of course you have a similar thing with alpha. Alpha should also scale with omega, but only if omega is weak. But if omega is large, it should
And
not.
what is the scaling?
That is that goes
Alpha
with the same
versus
scaling
omega.
of Q. So it's a product of these two scalings.
Because we also have in the theory the scaling.
Yeah.
Could I show?
Yeah. But so as I said, Q is that was simply the product of these two scalings. Both of them. And we assumed them in a range of between 0 and 2. If you include this uncertainty, the overall conclusions don't change. The numbers, of course, change. Maybe you need to send this in. What?
Or maybe you will find
Yeah.
a paper in 1995.
Which one? Yours? Oh, of course.
It was
Yes.
my calendar.
Just put it back in again.
What, but it's strange that it's very strange. It's really no time. it.
Yeah. Could you give me just put it in the thing? Yeah.
Oh.
This one.
Yes. Ah, okay. 95 installments of physics.
No.
Learning was Makin Lukashevsky.
Okay.
Like this one.
So here's the paper.
The paper is okay. And the page 162. Okay. Next one. 162. Yeah.
162.
Yes.
Yeah.
Okay, fine. Okay, this is estimation of saturated level of magnetic field, and we see here there's a scaling with angular velocity is like omega is ds. And we have also scaling of alpha. Alpha.
But this B field?
Yes. This is correct. Yeah, and alpha. Scaling alpha is omega 1 half. So from here we obtain that this is scaling with field is 2/3. So alpha scales with ds 2/3. So n equal to 2/3 from theory, and this is, we can compare with your numbers, is of the same one, I see.
Eta scale, where's eta?
Hmm?
Where's eta again?
Sorry?
Where is the scaling of eta?
Eta, you mean from viscosity versus rotation?
No, where's the speed field?
Here we take into account dynamical nonlinearity.
Yeah, so it's
because
not.
the evolution of magnetic helicity, and this is the main nonlinearity.
But then back to Fritz's question, he was asking how does the dynamo saturate? I was saying because the magnetic diffusivity increases with the B field faster than the alpha effect increases.
No, but here main nonlinearity due to the evolution of magnetic helicity.
Yeah, but then the alpha must actually decrease with the field strength, not increase.
We see that here alpha scales as 2/3 ds. Yeah, so you mean it's not okay.
It's not
Okay.
so maybe that's kinematic or not?
No, it's nonlinear.
But how can it saturate?
Okay, how it's considered? Of course, this scaling is more complicated than I said here, because we have here also diffusion parameter in some form. Of course, it's maybe very rough
Yeah.
scaling, but so
Yeah. I mean, it would be good if that theory actually does explain that.
yeah.
You check.
But at least, yeah, omega is a function of b, this exponent of unity, and alpha scales like that. So
Yes. You already had some things you wanted to show,
that's
right?
what we have.
Yes.
Okay.
There's a paper in Master PhD that Decipher and Pekin, they show that you can make stellar dynamos without alpha effect.
Yeah, but that's already known. I mean, what big, we know how big we know how big the omega cross J effect is. That's correct. There was a paper by Pekin and Seehofer this morning which said that you can make an alpha effect you have differential rotation, you have an omega cross J effect, and of course we know it works. We also know how big it is, but they don't actually discuss it, but it has been discussed in the literature since '88. It is known that the omega cross J effect for a given alpha effect is subdominant. It's very well known. Sasha, does this answer your question?
What?
Does this answer your question?
No, I'm just wondering what maybe we can get better fit of relational data if you use that dynamo theory.
Yeah, but it's a little strange because omega J effect is very weak if we have alpha in comparison with the action of alpha. Yeah?
I think so, yeah.
Yeah.
Well, alpha effect based again and over time, how do you know how big alpha effect is? How do you know this?
From simulations. From simulations we know it.
I mean, Petri showed already simulations that the alpha effect does exist in systems with convection. If you don't believe that, one has to come up with solid arguments against that. They need to be measured, and the counter arguments need to be addressed. One of the counter arguments is that if you just measure an alpha effect by just imposing a magnetic field, you don't actually know what is actually happening within the box. You may have a saturated dynamo already in operation. And then you can get different alphas just depending on what the field is inside this box. These are all papers that have been...
Catastrophic quenching, we don't know.
Sorry, what?
Catastrophic quenching.
Yes, of course. Catastrophic quenching operates. Catastrophic quenching operates. This is what helps us in interpreting the observation, the measurements. Catastrophic quenching is what is going on. Catastrophic quenching means the alpha effect is a function, is dependent on the magnetic helicity. And depending on what your helicity fluxes are, the alpha effect will be corresponding. So if you do it in a periodic box, for example, clearly alpha effect must go down. We know this.
So you think that this model by the Heifer and Picken is incorrect?
Yes, I mean, it's an ad hoc model. It's an ad hoc model.
If
The assumptions are unjustified.
I'm just wondering, maybe the theory fits better to observations, we don't know. Because we just presented theoretical arguments with our
But this is another possibility. Omega J effect is another possibility.
Yeah, okay. So since we have some observations of other stars, some trends as Axel showed, and we have some mean field theoretical framework for the sun, and we know that we have some things that work pretty well for the sun. Let's try to apply this to other stars and see if we can retrieve some trends that we have in the observations. So I will not talk about this. We know about all this. Oh yeah, that's fake.
That's not good.
Contact is not good. Yeah.
Maybe we should move a lot of this.
It's adaptive.
Maybe I should make it.
Yeah, sometimes it works. Maybe it doesn't.
Oh, okay. Okay, if you hold this. Okay, that's just to show you again the magnetic solar cycle. We don't really want to go through this again. It's so this is the sketch I showed you before, and one of the nice model now that is used is the Backup-Layton model, where the source term for a colloidal field relies on the tilt angle of active region when they emerge. And what is also nice with this model is that they use the meridional flow, which is observed. So there are some observations of the sun which are really used in this mean field model. So we may think that there may be something here which could, in theory, apply to the sun. So if you solve the equations for the vector potential and toroidal field, you want in this Backup-Layton model to model the source term which is responsible for the regeneration of the colloidal potential. So you have this S here, which is confined at the surface and which is more or less, which is completely even, function of B phi at the base of the convection zone. Because we think that active regions popping up at the surface are related to toroidal field becoming buoyant at the base of the convection zone and rising to produce these active regions. Sorry?
Why does it still need alpha-tone?
Yeah, this is because it's a general way of writing things. You can still have an alpha effect in the convection zone if you want, but in the cases
it's not about Layton, right?
Sorry?
Is it in Layton's theory, alpha-tone? I think you don't.
No, it's in the really purely Becker-Clayton flux transport dynamo. You don't have you replace the alpha effect by this source. But why not having both effects in the model? It could be
Actually, Mosumi does.
And some people think
Mosumi Fati does that. You put an alpha effect at the base of the convection zone. And
yeah, you can have alpha distributed in the whole convection zone, or at the interface, and still have a source term at the surface. Because Mosumi did this because it fixes the problem of parity, which we have with the Becker-Clayton model. We switch to quadrupolar parity very quickly.
No.
In what they show.
If you trigger the wrong, your set of
Yes,
parameters
but
is.
in the set of parameters they have, apparently they always get to this parity. So I don't know exactly. But I think we can probably have ranges of parameters where it's fine.
Sorry, the function S is not local, yeah?
It's not local, depends on the file base.
Actually, I asked about the last term. It is just this term include just by hand.
Yeah, because it's 2D axisymmetric. You need to add something to really get the dynamo to get colloidal field being regenerated.
Just about the last term.
This term or in the toroidal field?
No, this term.
This one, yeah, it's put by hand, yeah. It's prescribed as a function of B phi at the base and some product of latitudinal and radial functions to define it at the top. So it gives some results which you probably all know. This is just the northern hemisphere, toroidal field at the base, and we see that you can recover nice butterfly diagrams. This is colloidal field in the meridional plane, just the northern hemisphere. This is toroidal field. When we use this is the standard Becker-Clayton model. When we use meridional flow, which is just a single cell per hemisphere.
Really, you have not Becker-Klein here.
Well. Yes, because you have you prescribe your differential rotation to be differential here, and here you have a rigid rotation. So you really have you fix the thickness of it and. No, this is a Becker-Clayton model. So the source term of colloidal field is here at the surface, and that you can see actually that's. The colloidal field starts at the poles, then it's affected by the meridional circulation, and when the colloidal field gets closer to the tachocline, the omega effect produces a toroidal field, which is also advected towards the equator here, and this is what is shown on the butterfly diagram.
Why does it penetrate below tachocline?
Sorry?
Why does it penetrate below tachocline?
Oh yes, this is something we can argue how far it penetrates in the tachocline, this meridional flow. This is
meridional.
Yeah. So
what's the diffusivity?
Well, diffusivity is 10 to the 5 times 10 to the 10 in the convection zone, and it drops when we reach the radiative zone. We have a step we prescribe the diffusivity as well.
You have diffusivity below tachocline, right? You can see the signs.
Yeah, you have a step from 10 to 9, same as breakfast. Yeah, anyway, so this is just to show that these Becker-Clayton standard models can reproduce quite well what we have for the sun. But we did some experiments with Sasha during my PhD where we tried to introduce some more complicated meridional flows to see what it does, because on observations and both on observation in 3D models, we get some complicated meridional flows like this. So in this case, and with the same parameters, we get to a period which is much higher. So we make the advective path longer. So that's why the field is the period of the cycle is much longer in this case. But we can still get back to a 22-year cycle, which is shown here. But the butterfly diagram is quite strange, not resembling really what we have in the sun.
Are you using a different alpha effect besides the Barco-Clayton?
No, it's just pure Barco-Clayton source sum at the surface.
Then we set up the parameters such that when we compute the critical dynamo number, we do excite the dipolar solution and not the quadrupolar solution.
Right. So this was for the sun. We have a model which is working more or less fine in some range of parameters. So let's try to apply this to stars. So this is well, just to show you that that we have some measurements of the X luminosity in stars, which is a good proxy for magnetic activity. And we have kind of a relation between soft convection in the upper layers and X luminosity and then magnetic activity. So we're interested in these ranges, solar type stars, and how we could apply these Barco-Clayton models to this. So yeah, this is what Axel was talking about, the observational projects, which consisted of looking more than 100 stars. So it's F, G, and K type stars. And we have this particular trend, so we can probably wonder if it's really a real trend, if it's not going to, if there are several branches, as Axel said. But we still have this positive slope here, which corresponds to the fact that the further you rotate, the faster your magnetic cycle will be with this particular dependence. So this is the observations, and if you continue, as Axel showed already, so I don't think I'm going to talk too much about this. If you, it's again for two of the branches he showed, you recover the same type of dependency. So let's see what happens if you compute a Barco-Clayton model for this. So just another thing is that we have now some very nice observations thanks to the Espadon and Narval instruments, where it's in this paper they are looking at stars rotating at different rates, as you can see here, from so the sun 24 to 8.8 days, and what they see is that there are some big differences between poloidal magnetic energy and the toroidal energy. So if you increase the rotation rate, you will decrease a lot the part of the poloidal field acting in the total energy. So this is also shown here. This is for a star rotating at 22 days, and this is 8 days. And what they show here, this is the radial field, this is the azimuthal field, and they show that both are increased when you increase the rotation rate, but the toroidal field is much more the toroidal energy is much more increased than the poloidal energy. So there is a ratio which changes a lot when you increase the rotation rate. So this is also something we can check in our models. So this is what I told you. How could we reproduce this particular trend of faster rotators have shorter magnetic cycles. Can we reproduce this increase of toroidal versus poloidal components? And so with the kind of Baker-Clayton model, maybe we can apply this to stars. So this is just to show you the dependence of the cycle period on the different ingredients we're incorporating in our Baker-Clayton model. So what is already very clear here is that we have a slight dependence of the cycle period on the rotation rate. So this is maybe not very good. We have an enormous relation between the cycle period and the amplitude of the meridional flow. Of course, this is a big. This is the major feature in these Baker-Clayton models. So what would be interesting, of course, is to know how the meridional flow depends on the rotation rate, and see how we can adjust to the cycle period in this case. So to do this, we looked at 3D models, so that Ben Brown and collaborators did in Boulder, so with the hash codes that Sasha told us about yesterday. You have here more or less the sun, I think. It's one rotation rate, yeah, and this is at 5 times the rotation rate of the sun. So you have here the radial velocity. You see that you have some what they call active nest of convection. You can see here that is strongly non-axisymmetric, of course. You have here rotation, the mean rotation, here and here, and you have here the meridional flow, which is multicellular, very complicated, and with some cells which are, I think, poleward here, equatorward here, blue is equatorward at the surface, and red is poleward at the surface. So you have this particular trend for the meridional flow. So what is important here to highlight is that as you increase the rotation rate, you decrease the meridional flow. And this is the energy, kinetic energy of the meridional flow. So this is something very new, because before some people tried to apply some alpha omega dynamos to see if they could recover the trends we have for other stars, and they were always assuming that the meridional flow was dependent on something like omega or log omega, and here we see that it's the contrary. When you increase omega, the meridional flow is decreasing, in fact.
I mean, this is, of course, also in principle well known. This is just Taylor-Proudman theory. Taylor-Proudman tells us that the angular velocity, angular meridional circulation must go down. We also have such a result in our 1990 paper from Wingfield models with Zonda effect.
Yeah, so why are
so
people
why did
using
Paty and
these?
the others did the reverse?
I mean, they did a few other things which were contrary to the literature. They, like, for example, I mean, the boundary condition, for example, is an unphysical one, as
We discussed that
is one thing, and the functional form of the alpha effect is not regular near the pole. But you can ask me why, but I told you that because I don't look at this literature. It was discussed.
Yeah, so do you know if there's what are the physical reasons for assuming this kind of scaling? There's not really
No, I guess we just said it
It's
rotate
just
faster, we
which
should
way?
get faster flow.
Yeah, of course the opposite is the case, as you show here
Yeah.
also. Yes, it's clear. But what is the exponent here? I think it's minus 100 something.
yeah,
or
what's the exponent again? It's,
I think that we find that for the for the energy in meridional flow, we find it to be scaling as 1 over omega. But when you, so if you take the square root of that, we find minus 0.5. I don't know what you are getting.
I think 0.5 is what I just said, yeah? So that was also what I think.
So what did
Fritz, do you know this? What do you get?
Yeah, I mean, it certainly goes down strongly. I don't know the exponent.
I mean, this was a paper which is on in GAFD.
In GAFT, okay.
Yeah, which means
no
FR now.
So you published in 1990?
91, I think.
1990.
It was first, by the way, rejected. I have a guess who the referee was on the grounds that we used exactly the same boundary condition as Dick Party and Paul Schaumann used 10 years later.
Ah yes, I remember.
So we used A equals B equals 0, which was first used by Roberts, by the way, himself in 71.
It was refused because of boundary
I mean,
conditions.
it was a few other things. It was all well known or
I
something.
think I have this paper.
Oh, and GFD paper?
Well, anyway, yeah.
Maybe I actually also have it because somebody scanned it for me.
So now that we have some trend for our dependency of the meridional flow with respect to rotation, we can introduce all these ingredients back in our backlocated model with a single cell for the moment. We're just trying to introduce all this in the standard backlocated model, which gave us nice results for the sun. So if we do that, we see that this is again the rotation rate. When you increase the rotation rate, the ratio between colloidal and toroidal field is decreasing, as in observation. So this is pretty nice. This is pretty understandable because we have increased the omega effect. So the toroidal field is much more amplified than the colloidal field. We didn't scale the source term with omega, and this we keep the same
alpha.
Yeah.
Yeah. How can it be if alpha depends on B in the base of the convection state?
Alpha depends.
Alpha is non-local, right?
Yes. Alpha depends on toroidal field. Well, yes. On the base of the convection term.
So the S term is modeling of the emergence of toroidal structure from the base of the convection zone up to the surface. It is thought that the tilt of the active regions from the east-west direction, this tilt is due in part to the influence of the Coriolis force on the rise of the structure. So if you increase the rotation rate, you can expect to have perhaps a larger tilt. It's not obvious, it's not perhaps as simple as that, but you could expect to have a tilt and so more poloidal component in the active region as the rotation rate increases. But we didn't take into account that scaling because we find that you go back to the... Can you come back one more slide? Yeah. When you look at the least square feet we did to the set of models, we find that P cycle is strongly dependent on the velocity field of the meridional flow, V0. And you see there is a very weak dependence on S0. So we wonder, we said that we were not sure that it will make much difference to vary this parameter given the very weak dependency of the cycle period with the source term. But of course, we should we can take it into account.
It may not change a lot on the cycle period, but it may change on the ratio between colloidal and toroidal field.
Definitely.
Depends on alpha also on the period. The period of cycle depends also on alpha.
Yeah.
But yeah, you see
alpha
is S for us.
S0 is
We
the
don't have alpha.
intensity of the source term, so this is very weakly dependent.
This is the source term of backcoplated
You have alpha in also.
No, I have just a source term on the surface, no alpha.
I'll just
This is a general scaling of when you take a backcoplated model, you take different set of models, you vary the amplitude of the source term, you vary the rotation rate, you vary the diffusivity, you vary the velocity, you get a bunch of models and you see how the cycle period depends on them.
Yeah.
And we find that there is a weak dependence on everything except the meridional circulation.
Yeah, and this is, I think, quite...
alpha, then it's only diffusion and meridional circulation combination of these. You can get cycle without median circulation, just with diffusion.
Yes, but we are in the we have computed our model such that they are still in the advection dominating
You
region.
can clearly see that here, that the period of the cycle will strongly depend on the advection path,
Then
of
just
course.
reversed circulation time with median circulation would be that, right?
Well, you fix it to be more or less the average of what is observed here, so about 10, 15 minutes per second.
What we find that it depends the most on is actually the amplitude of the velocity at the base of the convection zone more than at the surface.
Yeah, because the toroidal field is advected here.
Meridional.
Yeah.
Yes.
And do you have omega versus saturated field?
So in the show the
Omega versus?
the new plots for the new models when we try to adapt that to other stars.
Versus B.
Yeah,
Yeah. So this is what I was
as a function
telling you
of
about.
omega,
This is the nice part, because when we increase omega, we indeed decrease this ratio between colloidal and toroidal energy.
Colloidal to toroidal. And
Yeah.
do you have graph colloidal field versus orbital, or vice versa?
as a pure
Toroidal field
Everybody
versus
is
orbital.
increasing. Everybody is increasing in terms of omega, but the toroidal field is increasing more.
we have
I
perhaps
think water colloidal
let me
field.
see, we have perhaps that figure. Let me see if I have it.
Just in order to compare with theoretical conditions.
Yeah. Well, I don't really know exactly what the colloidal field is increasing.
I can look at it and see if we find something.
Meantime, I can ask. I can answer to Axel's question.
Maybe I can ask somebody beforehand. Anybody vegetarian for tonight?
Actually, I'm a carnivorous. I eat meat only.
Nobody, yeah? Nobody is.
Yeah, I'm an anti-vegetarian, exactly.
Okay, sorry, yeah, that was out.
Meantime, could I answer to your question? This is dependence of kinetic quantum alpha effect.
My question?
Yeah, and you said what is this is kinetic alpha effect. Mentioned consistently for the total alpha effect tends to zero, which alpha k goes
Yeah, but I remember
tends
so
to
for
zero
one.
in saturation.
Sure. And then?
Okay,
Yeah.
so this is real nonlinear dynamo predictions.
Yeah, but if you measure only the total alpha, not the kinetic alpha.
You measure total alpha, or the total alpha in saturated level tends to zero.
Yeah, not according to this possible.
Because dynamo number, nonlinear dynamo number tends to zero in saturated state.
Of course.
You cannot measure total
yeah,
alpha.
but in our case it works because eta goes large.
Okay. So this is different model. But at least this simple model with taking into account dynamics of magnetic helicity yields scalings which are in agreement with your
With observations? I don't know.
yeah.
Obviously not. If the total alpha goes to zero, then it can't increase with omega to 1/2. I mean, I see now there's a disagreement.
Yes, I think so too.
Disagreement?
Yeah, between your model and
Why? It's not disagreement. It's usually in a linear dynamo, when there is saturations, total alpha should tend to zero. Dynamo, nonlinear dynamo tends to zero.
I accept
My
that,
interpretation
but
was
not
based on
his model.
Not his model.
Yeah, right. My interpretation may be wrong, of course, but is there a better model which actually reproduces those observations? I mean, what does this now say about the cycle frequency?
Yes. Oh, okay.
Probably comes later, right?
Okay, so this now, let's look at the cycle period now, and not surprisingly, as we increase omega, we decrease the meridional flow, and then we increase the cycle period, which is contrary to what is observed in fact. So this is some examples of different rotation rate. This is a half of the solar rotation rate, and this is 5 times. And with 5 times the rotation rate, the cycle is very low, and the magnetic field is reversing. It's reversing in a much longer time scale. So we have the wrong sense.
So
of
the first
dependence.
conclusion is, if you take the scaling, which is what we believe it is, the backup Clayton fails to reproduce stellar data, at least for the active and
Because it's
inactive
so
branch,
dependent on
not for
the
the S branch.
According to our plots, at least, because the one by Ola, Katarzyna Ola, is of course disagreeing. Which she made.
It's the other
Yeah,
direction.
it goes the other way around. That's what the plot I showed you. That
Yeah,
was
but I
this.
thought it was going the same
No,
direction.
no,
so
no, no, but
because the curve was all like
Yeah,
that.
but it's
So
not the frequency.
yeah, but in one no, wait. In one case, it was the cycle period. In one case, the 1 over the rotation frequency period.
ah.
So it was different. That's what I was trying to emphasize. That this
Okay.
disagreement.
No,
I have-
no.
I
They
have-
perhaps screwed up their labels, no?
What?
Did they?
No.
They actually
we
argue that they find
we
the
reproduce
opposite.
this. We reproduce this. This goes back to earlier papers also as well. So their result is nothing new. It's just that we don't believe that.
They're mixing
They,
up too
they
many
took the
things.
same observation, yeah, but they're
They are
mixing all
mixing up
together
things.
because they have just one branch.
That's sort of the
Okay.
statutory and
Be careful making such conclusions about Webber-Clayton theory that they reproduce, because that's your interpretation. Webber-Clayton theory doesn't include meridian circulation at all. It's a diffusion.
Flux transport.
So
Let's call them flux transport dynamo.
yeah, so that's a particular interpretation with some constant.
Well, in the case where
the source
we're
code and,
trying to look at a model which is fine to reproduce a solar cycle, really. If you just have something dominated by diffusion, the equatorial branch of migration of the sunspot is not very well recovered, I think.
I wouldn't call it testing Webber-Clayton model, because it is only particular implementation.
Okay, so you mean flux transport dynamic?
Yeah,
What do you mean?
Because it keeps the same source term, that you don't have alpha here, and you don't
Yes,
have.
but in the backup Clayton model, which
In Webber-Clayton
is
model, the length of the cycle is determined by diffusion.
well, okay.
Not in a recent, not, Sasha, not in a recent. The idea is the following. The current solar mean-field model to recover the solar cycle and most properties, like the quadrature of phase between the toroidal field and the toroidal field, is so-called the flux transport Backup-Clayton model. Okay? If you take this flux transport Backup-Clayton model and you apply it to stellar data, it doesn't work. You turn it as you wish, but it does not work.
This particular implementation of this model, not the whole idea.
So what?
Let me finish now. Webber-Clayton model, the length of cycle controlled by diffusion, which is
Not the latest versions. The latest version,
Let me
they are
finish, Sasha.
advectively
Sasha,
dominated.
can I finish? Okay. So it's controlled by diffusion. It's calculated from a supergranular diffusion. And when you do fast rotation, you change the structure of convection, and you can calculate the diffusion time for fast rotation. Then you get a new cycle. That would be testing of at least this part of the Webber-Clayton theory.
Yeah, okay,
This
so
particular
we should say
implementation,
we test the
the
flux
party
transport
implementation of
Backup-Clayton
this,
model.
that's different from this.
Well, no, I think the idea was to test the model which is now more or less shown to work well on the sun, and which is used to make predictions, even stuff like this. Yeah, Dick Patrick tries to do prediction with this exact model, with just alpha at the surface.
That's a big party human model.
Okay.
Well, it's interesting to make such chain of conclusions.
No, but I think it's true that most flux transport
I will still say the same thing, even if you disagree. I disagree with you, I don't care. I think this is the current model, and the current model is like Backup-Clayton is the source term at the surface, and then you have an advection path, and these are the advective dominated model. We are not speaking about the diffusive model. And in the conclusion of the paper, we also advocate that we need to get something new, and that can be, for example, turbulent clamping to transport the field. So, to some extent, I go back to what you are saying. If you have another mean of transporting magnetic field from the surface down to the tapered line, and you take out the meridional circulation from this picture, then of course the type of model will not depend as strongly on the meridional flow, and you can perhaps recover the cycles.
I made this calculation with pumping.
Yes.
Yeah, it's you.
Yeah. So you're Guerrero?
Yes, I am.
Okay. But yes, and we cite your paper because we think that's a very nice paper, and we say that the other option is to implement your turbulent pumping, and by implementing your turbulent pumping, it seems that your
the period depends more on
much less of V. You find a scaling that is now minus 0.1 instead of minus 0.9.
Yeah, but
so
I have a question about this. Is your meridional circulation occupying the whole convection zone?
In one model, yes, but not in I have two models. In one of them, it's occupying all the convection zone, and in other only, it's a very shallow.
And you find the same reduction of the dependency, or?
Sorry?
You find the same reduction of dependency on V?
Yes, yes.
Because of course, if you concentrate your meridional flow in the upper layers, it will be less dependent, because the important thing is at the base of the convection.
No, but I don't remember.
It would be nice to have the scaling for the two cases. If you can find that in your data and give it to us, that we could perhaps, when the referee comes back to us, be a bit more specific in our conclusion discussion part with your work. So I would like to know that. Yeah. I met your former PhD advisor in Rio.
Okay, so if well, we like the bifurcated models. So we're trying to rearrange things.
I'm not asking you if you like or not.
No, well, so we try to rearrange things because we know we maybe didn't include everything. We just changed the rotation rate and the meridional flow. Maybe there are some other ingredients we don't take into account, and let's try to improve our model with some different ingredients. So this is what we're doing here. For example, we didn't vary the differential rotation with respect to the rotation rate. So this is maybe something which we have to take into account. And this is what we did. So we took some dependency which is quite strong, because we wanted to more or less to have the maximum dependency. I'm not sure we have really clear ideas of what the dependency here is. You said 0.3 here. This is observational.
0 or 0.3.
Yeah, observations tell that it's really increasing this function.
No, that observation are not saying anything. It's a total mess. But delta prime over omega is then 0.3. I don't think it's delta prime which is 0.3.
No,
delta prime is 0.7.
Well, the slope from observations for the relative rotation is something like 0.7, 0.8, which would indicate plus 0.2.
Okay, so you think it's a relative, so I thought that it was the reverse. I thought that was the relative that was 0.3 and the absolute that was 0.7.
No, the other way
the
around.
absolute is very, very small. And
not in the Balunas work. Not in the work by Donahue et al.
No, I'm not referring to those ones. I'm referring to Hall, Henry papers. Do you know this?
No,
yeah,
it was a work by Barnes.
The other way around. That could be true, but this was earlier than that, and so it's the
Henry was 1995.
The Cameron work, or the group
Yeah,
of
that's
Barnes
zero.
and things like
Yeah,
that.
exactly.
So
That's
Barnes say that there is almost no dependency,
Yes.
and Donahue et al. Say there is still a strong dependency. And when I talk with Steve Starr, he says he doesn't believe Cameron works, and when I speak to Cameron, he says he doesn't believe Steve Starr works. So we have to sort out things. So we say let's take the most extreme dependency of the differential rotation with rotation rate.
You should include both cases. You should include no variation, and then you should investigate how does your model change when you include the variation.
No, we did that with no variation, and we know it's not working.
Yes.
And so now we
maybe
do.
It is implying that you need some excess of different rotation.
Maybe we need something more.
Yeah.
So probably we can also try to vary delta omega the scaling with omega, but what we find is that there's almost no action on the cycle period here. There's an action on the ratio between poloidal and toroidal field, of course, because here you increase a lot the differential rotation than the omega effect, but you don't change the cycle period. Doesn't make it
right, and maybe you should also try a non-axisymmetric model as well, because when you increase the rotation rate, we know that the stars tend to become more and more non-axisymmetric as well.
What? No, more axisymmetric.
No, more non-axisymmetric, I think.
I mean, if the differential rotation goes down, then that may well be possible. The only reason why you tend to favor axisymmetric models is because the differential rotation is strong. But that's not the case for rapidly rotating stars anymore. The differential rotation goes down.
Yeah, with respect to the alpha effect.
What?
That's not completely
yeah,
clear,
but Sasha, here we have to make the distinction. Relative to the alpha effect, I mean, the alpha effect is also increasing the rotation, so the relative strength of the differential rotation, even if this would be completely constant.
Okay, so you mean that we are switching from alpha omega to alpha square type of model? That's your point. Okay,
yes,
this is slightly different. Yes, okay. Restated like that, I agree. So.
Okay, so the conclusion here is that adding this this dependency of the differential rotation with rotation rate, which is maybe not the right scaling, but anyway doesn't do anything on the cycle period really. So what we thought is that since we have such a dependency on the cycle period on meridional circulation, maybe we should try to have different meridional circulations. And this is something which could be seen on 3D models. You have very complicated multicellular meridional circulations with, I think, sometimes if you average, you can recover a cell which is poleward at the surface and equatorward at the surface here at higher latitudes. So we try to introduce a different meridional circulation and see what it does. And indeed, of course, it reduces a lot the advection path, and then for a 5 times solar rotation rate, you recover something which is much closer to observation. You indeed decrease the cycle period in this case. So before we had, when we were just using a single cell, we had about 20 years for the cycle period. Now we dropped to about 5 years. So this is something which seems to improve a lot of things in this backup flux transport backup latent models, which are so influenced by the meridional flow. So this is maybe this could be maybe something explaining why things are like this.
I have maybe a very naive question. Why it's so important to obtain a cycle with period of 5.2? Because really,
no, this is not because it's a success. It's just because we managed to shorten a lot the cycle period compared to what we had before. This 5.2 is not really important. It's just we tried to get to as close as we could to observations.
Because observations exist, I think, essentially a long period of the cycle.
Well, I think if you try to look at Axel's observations and curves, you see that for 5 times the angular velocity, you get to do something like 3 years for the cycle period, or something, or 3 or 4 years, but it's not very clear. So
not 20 years.
We are a little bit too high, but if we play on the extension of this meridional cell, we can get to a better agreement.
I can see that multiple cells are not observed on the sun.
They are not observed. Well, there were some observations showing a contour cell at higher latitudes, right? In cycle 23.
It's only from around 30 regions, and it's only
Around
and they don't reverse the flow. Direction is still the same. they slow down.
Well, this
So at the
is not clear
surface,
at
maybe,
all.
but if you go deeper down, there were some.
But also,
well, I
if
don't
you look
know
at,
about it.
if you look just at, butterfly diagrams that what, in your plot, when you see diffusion, transport of magnetic flux, you transport it, continuously to the polar regions. If you have multiple cells, you would not transport, this way. You'll see picture like in your simulations.
Yeah, you mean here at higher latitudes?
Yes, yeah, and
Or
you
here?
can see on the sun, you can see this all transported, all the way to the polar regions.
Yeah, but maybe
picture,
on
your
the
first
star,
slide,
it's
your
not the
first
same
slide,
place.
yeah, but that's
Maybe it is just a
it's a qualitatively different picture of solar cycle, and
Yeah.
multiple cells.
But I think the idea was to show that the only way to reconcile really, or at least what we saw, that to reconcile Backward-Clayton models with observations of sun-like stars was to act very strongly on the meridional circulation.
But this still will have the same problem that if you increase the omega, the meridional circulation will go down and gives the wrong dependence.
Yeah, but here just for this particular case, I kept the meridional flow to be weak compared to the one solar rotation rate. So I decreased the amplitude of the flow, but I changed the profile of the flow, and it in case is better.
Because it's happening on this shorter circulation, right?
Yeah, exactly. You just shorten the advection path, and well, this I think may occur in the start.
Okay, there is other observed quantity which can be compared with any dynamo model, like X-ray luminosity versus large-scale numerically. Do you have predictions for such scaling?
We except of the amplitude of the magnetic field, and if you make a proxy model from the amplitude of the magnetic field to get the X-ray luminosity, then we can give you something. But we didn't play with that aspect.
Axel and you? Have you compared X-ray luminosity versus large-scale magnetic field? From your dynamo?
So these are scalings which have been studied. Also, UV scaling, for example. That actually all goes back to a famous paper by Wilho, 84, while he was at Nordida. Cosmic Wilho. So there are power law scalings, simply, between B squared, or between B over B equidistant, if you wish, and then your X-ray luminosities. If you scale this to volumetric, of course. By the way, that's when I say RHK as opposed to FHK, that the R means it's relative. It's relative to volumetric. That's why it's called R, and not F, which is a flux.
I think that's it. Yeah, it's just the conclusion is that since these models are so dependent on the meridional flow, the only way to reconcile it with what we have in the cycle period is so dependent on the meridional flow is that we can only act a lot on the meridional flow to reconcile it with observations. And yeah, maybe so with your model we can have something which cycle period which would be less dependent on the meridional flow, and that is a very interesting feature. I think if you introduce another way of transporting the field, then it improves things. So.
It's very interesting, but it was made with inconsistent. Numerical simulation, it's not a single cell.
It was efficient.
Yeah, that was a distributed dynamo.
Yeah, so it's working equally well, I think.
Say that unicellular scaling is from this simulation, but these simulations don't reproduce unicellular diagonal flows.
We don't
So
know.
you cannot really use for scaling for unicellular model.
Well, you mean we don't know where the amplitude will be maximal or something?
Yeah, I don't know what will happen, but because this model don't reproduce, the unicellular circulation, and you cannot really use for scaling unicellular model.
But I don't believe the
Just
inversion right now. So you believe your inversion, I don't believe you
No,
inversion of the meridian flow. You know?
Sasha, nothing to do with inversions. It's just internal consistency. You take a single cell model and scale it with a model which cannot reproduce it. It reproduces only multi-cells. Your simulations always produce multi-cells, right?
Sometimes we have a one cell model.
Yeah, but when you have one cell, then you should scale in a one cell, because you cannot scale one cell model with multi-cell
And
simulations.
what we find that as you increase the rotation rate, you get more and more cells. If you start with one, you do get more as you increase the rotation rate.
But you cannot
If you start with
No,
two,
but
you
the
get more.
conclusion is still that if you have a multiple cell
just internal
parallel cell, it
consistency
makes
of
it
the
better.
argument.
And now there is a different thing. In terms of fluid dynamics, as we discussed with Flat earlier, it seems that from fluid dynamics, you do find that the meridional flow reduces in amplitude in all of the models. So you can say that you don't believe any of the models, that's okay, but we all find the same trend. As you increase the rotation rate, we increase the delta omega, but we reduce VP, the colloidal velocity. So that we can take and see what that does.
Actually, it's not necessary to believe in your argument. You must be consistent. You must be consistent. You cannot do what, just inconsistent conclusions.
But I'm consistent? Why I'm not consistent?
Because, what I'm saying is that, you try to scale single cell model when you don't have it, you have only multi-cell.
I'm
You say you cannot reproduce it, you cannot even reproduce it, when you have
the kinetic energy and the
No, but the thing is that this single meridional flow is used for the sun, and it works well for the sun apparently. So why shouldn't it work for other stars?
No, it can work, but you cannot scale numerical simulations that are multi-cell.
But what we are using is the content of kinetic energy.
It's just simple logic,
It's simple logic. I'm telling you, I'm not using the profile. I'm using the content of kinetic energy in the meridional flow. Independently of the profile, the content of kinetic energy